So we have something interesting going on. I have this ring of conductor right here, this square ring. It has a resistance of 2 ohms. We see that it is 2 meters by 2 meters. So the area of this ring would be 4 square meters. And we see a magnetic field going through the surface defined by the ring, and it's constant. It's a constant magnetic field of 5 teslas, and it's going exactly perpendicularly to the surface of the ring. Now, what we're going to happen, what we're going to see happen is over the next 4 seconds, and this is going to happen at a linear rate. It's going to happen at a constant rate. We're going to see the magnetic field over 4 seconds go from 5 teslas to 10 teslas. So it's going to double over those 4 seconds. And by doing so, we're going to have a change in flux. Let's think about what the change in flux is over this 4 seconds. So our initial flux, let me write it over here. So flux, let me just in a different color. And at any time, if you are so inspired, I encourage you to pause the video and figure out what our change in flux is. So our flux initial is going to be, well, it's going to be the constant magnetic field. You could say the average magnetic field over the surface, but since it's constant, that's just going to be 5 teslas. So 5 teslas. And it helps us in this problem that the magnetic field vectors are exactly perpendicular to the surface defined by the ring. If they weren't, we would have to find the component that is perpendicular. But we have that right over there. So we have 5 teslas. That's the average magnetic field, or the average component of the magnetic field that is perpendicular to the surface. So 5 teslas times the area of the surface. So times, well, 2 meters times 2 meters is 4 square meters. So that is going to be equal to 20 Tesla meter squared. Tesla meters squared. Fair enough. Now what's the final flux? The final flux final is going to be equal to, well, now the average magnetic field, or the average components of the magnetic field that are perpendicular, and the way I've defined this magnetic field, the vectors are already perpendicular, is 10 teslas. So 10 teslas. The area of our ring hasn't changed, so still 4 square meters. So times 4 square meters. And so what is this going to be? So our final flux is going to be 40 Tesla meters squared. So what is our change in flux? Let me write this over here. Our change in flux, which is going to be our final flux minus our initial flux, is going to be 40 Tesla meter squared minus 20 Tesla meter squared, which is just going to be 20 Tesla meter squared. So we figured out the change in flux. We actually know the change in time. It's going to be 4 seconds. And actually using that, we can now figure out what the voltage induced is going to be. The voltage induced, or the voltage that's going to now induce a current. And if you were to look up Faraday's law on the internet, you would look up for a formula for Faraday's law, you would see something that looks like this. You would see voltage generated is equal to negative n, at least if you're not using the calculus version of it, negative n times our change in flux, change in flux, not just flux, change in flux, delta flux, over change in time. So one way to think about this, and to do this problem right, we're assuming we have a constant, or the rate of change is constant in our flux. So you have your average rate of change of your flux, and then you're going to multiply it times n. N is actually the number of loops you have, or you can think of it as the number of surfaces defined by it. In this exact example, n is just going to be 1. We just have 1 loop, so that simplifies it right over there. And then, so this is going to be, and you might say, what is this negative? Because it's a bit of a strange thing, because, how are we defining direction, what's in, and all of that. And that's why I'm not a huge fan of this negative sign. This is, if you look it up in a textbook, they'll often say, and you're not using calculus, they'll say, oh, this reminder to use Lenz's law. They'll write literally Lenz's law. And I would say if they want a reminder to use Lenz's law, why don't they just remind you to use Lenz's law instead of putting a kind of bizarre negative sign there? And the negative sign actually does make sense if you were doing kind of the using the vectors here and taking and using a little bit of doing more sophisticated mathematics. But this is just saying that the voltage induced is going to be in a direction, so to induce a current whose induced magnetic field will go in the direction, will counteract the change in flux. So that's just Lenz's law there. So the real key here, is, at least for this example, is to find our change in flux over change in time, or our average rate of change in flux. And what is this going to be? Well, this is going to be 20 Tesla meter squared. 20 Tesla meter squared. That was our change in flux right over there, divided by our change in time, which is 4 seconds, over 4 seconds, which is going to be equal to, and I could throw that negative there if we want to, that negative 20 divided by 4 is 5 Tesla meter squared, or squared meters, per second. And this actually turns out to be a volt. So we could say this is negative 5 volts. Negative 5 volts. Negative 5 volts. So if you have a voltage of, well, let's just say 5 volts. We can think about the negative later. If you have a voltage of 5 volts across a circuit that has a resistance of 2 ohms, what is the current going to be? Well, we just have to remind ourselves V is equal to IR, or voltage is equal to the current divided by or voltage is equal to the current times the resistance, or you could say that the current is equal to the voltage divided by the resistance. So in this case, the current induced is going to be the voltage, and I'm just going to focus on its absolute value now. We can think about its direction in a second. It's going to be its voltage, 5 volts, divided by the resistance, so 2 ohms, which is going to be equal to, this is going to be equal to 2.5 amperes. 2.5 amperes. So we now know the magnitude of the current that's going to be induced while we have this change in flux. Remember, this is going to happen while over the course of this 4 seconds, as we have this rate of change of flux, this average rate of change of flux, which we'll assume is the actual rate of change of flux. We're assuming that it's changing at a constant rate. And so while it is changing, we were just able to figure out that it would induce a current of 2.5 amperes. Now, the next question we should ask ourselves, and this is where this little negative comes in, is a reminder for us to use Lenz's law, is, well, which direction is that current going to go in? Is it going to go in, let me pick 2 orientations, is it going to go in a clockwise direction? Is it going to go that way over the course of this change in flux? Or is it going to go in a counterclockwise direction? Is it going to go that way? And to think about that, we just have to use the right-hand rule. Take our right hand, point our thumb in the direction of the proposed direction of the current. And so if we went with this one, our right hand would look like this. I'm literally taking my left hand out, my right hand out, and I'm drawing it, and I'm looking at it to think about what would happen. So that's my right hand. So if I use the right-hand rule, if the current went in this direction, then it would induce a magnetic field that went like this. And so if the current went in this direction, the magnetic field it induces inside the surface would only reinforce the change in flux. So it would only add to the flux. And it's going in the same direction as the change in flux, which would just keep us, as we talked about in the Lenz's law video, that would turn into just this source of energy that comes out of nowhere and defies the law of conservation of energy. So this absolutely is not going to be the direction. And so we know that the direction is going to be in a clockwise one. So the current, the 2.5 ampere current, is going to flow like that. And we're done. By thinking about our change in flux and how long it's taking us, we were able to figure out not only the magnitude of the current, we're able to figure out the orientation or the direction that is actually going to flow in.